right, so let's cancel out that volume. So with all of our volumes canceled out, now this step up here, this equation that is right here, equation 1, right there, that is an energy equation. Okay, that's all work and energy. Work and energy are the same thing. Now down here, this is pressure. Equation 2 has P1 minus P2, so everything better be in units of pressure. So let's check our units here. 1/2 rho velocity squared. So density is measured in kilograms per meter cubed, and velocity is meters per second. So velocity squared would be meters squared per second squared. So that's the unit you're going to get there. That's the unit you're going to get there. And then this guy right here would be kilogram per meter cubed. Gravity is meters per second squared. And then this would be meters for height, for y. So do you see you're getting kilogram meter squared per meters cubed second squared? Now let's check pressure. What's pressure measured in? Pascal, which is a Newton per meter squared. Remember, it's force per area, and a Newton comes from multiplying mass and acceleration. So it's a kilogram times an acceleration, meters per second squared, over meters squared. So I get what? Kilogram per meter squared seconds squared. Well, what is a kilogram meter squared per meter cubed second squared? Up here. Isn't that a kilogram per... Oops, I didn't cancel a meter down here, did I? Oh, shoot. So it's kilogram per meter second squared, and then I've got my kilogram, and this would be a meter second squared. All right. So I did that to show you that 1/2 rho velocity squared is in the units of pressure. So equation 2 is like a giant pressure equation. Okay, the difference in the pressure is going to cause a difference in speed and or height. Okay, it's going to cause a change in energy. Now let's rearrange this equation, and let's put all of our conditions for position 1 together and all of our conditions for position 2 together. So once you add get all the 1's together and all the 2's together, this begins to look like, I know it's not conservation of energy, but it kind of looks like the conservation of energy. If rho is like our mass equivalence, so do you see it there? There's the speed and there's the height right there. Now as fluid flows, the energy is constant. Whatever energy the fluid has in one position in the pipe, for this non-compressible fluid, it should be the energy it has later. That was equation 1 at the top. By dividing out the volume, we get a pressure equation. So what happens when the pressure decreases? So if this pressure were to go down, let's say the object goes from height y1 to y2 and there's no change. So maybe it's a straight pipe. So there's no change in y. What would happen to the velocity? If the pressure, if P2 goes down, V2 does what? It goes up, and that's counterintuitive. When you think pressure getting greater, usually you think that that means that the velocity got bigger. But actually, it's all about the conservation of energy. The velocity has to get bigger when the pressure gets smaller to balance out the energy in the mass of the fluid. So when the energy due to the pressure goes down, the energy due to the movement has to go up to compensate for the difference, because we can't lose energy. And this, my friends, is Bernoulli's equation. So Bernoulli's equation relates the pressure in one region to the pressure in the other region due to its speed and its height.